Hello dear students! In this video, we will continue talking about resistors. The new objectives which we will discuss in this video are: define equivalent resistor, determine the two formulas giving the equivalent resistance of resistors connected in parallel and in series. Before we start with the new objectives, let me remind you of Ohm's Law, which we discussed in video 1. Ohm's Law studies the relationship between three factors, which are resistance, voltage, and current. As resistance increases, current decreases. This is shown in two formulas, which are U equals R times I, where U is the voltage, R is the resistance, and I is the current. And the second formula that can be derived is I equals U over R. So as R increases, I decreases. Well, resistors are electrical components that can be grouped together. They can be either grouped in series, as this figure shows. R1 and R2 are two resistors connected in series across a dry cell, and they can be grouped in parallel, as this figure shows. Each grouping of resistors is equivalent to a resistor called equivalent resistor. What is an equivalent resistor? Here we have R1 and R2 in series. Each resistor carries current I. The voltage across the grouping is UAB. This grouping of resistors is equivalent to a resistor called R equivalent or equivalent resistor, which carries the same current I under the same voltage UAB. Similarly, we have R1 and R2 in parallel. The grouping carries current I. The voltage across the grouping is UAB. This grouping is equivalent to RE as well, carrying the same current I under the same voltage UAB. Then the resistor equivalent to a grouping of resistors is the single resistor, which when replacing the grouping carries the same current under the same voltage. Now, how to calculate the equivalent resistance of a resistor equivalent to a grouping of resistors. Let's begin with the first case where resistors are grouped in series. Here we have R1 and R2 grouped in series. RE is the resistor equivalent to this grouping. Since the two resistors are in series, then current I is unique. This means that R1 and R2 carry the same current, which is I. Also, RE carries the current I. What about the voltage? The voltage across R1 is UAC, and the voltage across R2 is UCB, and the voltage across the grouping is UAB, which is the voltage of the equivalent resistor. Then, to derive the formula, let's write UAB equals UAC plus UCB, which is the law of addition of voltage in series grouping. We will substitute U by RI, then we will get UAB is equal to R equivalent times I, which is equal to UAC substituted by R1 times I plus UCB, which is equal to R2 times I. But since I is unique, then we can divide this by I, so we will get RE is equal to R1 plus R2. Now let's verify this formula using an ohm meter. Here the resistor R1 is connected to an ohm meter. To measure its resistance, it indicates 50.8 ohms. When R2 is connected to an ohm meter, the ohm meter indicates 98.6 ohms. Now R1 and R2 are grouped in series and their resistance is measured by the ohm meter. The ohm meter indicates RE equals 149.4 ohms, which is the sum of R1 and R2. Then the formula is verified. Now let's determine the formula for calculating the equivalent resistance when resistors are grouped in parallel. Here we have R1 and R2 grouped in parallel. Then the voltage U is unique. This means that the voltage across R1 is UAB and across R2 is also UAB, which is equal to the voltage of the grouping. RE is the resistor equivalent to this grouping. Then the voltage across RE is UAB. If we use the law of addition of current in parallel grouping, we will get I equals I1 plus I2, where I is the main current, I1 is the current carried by R1, and I2 is the current carried by R2. If we replace I by U over R using Ohm's law, we will get, instead of I, which is I main, we write UAB over R equivalent, and instead of I1, we will write UAB over R1, and instead of I2, we will write UAB over R2. Since U is unique, we will divide by UAB to get the following formula, which is 1 over RE equals 1 over R1 plus 1 over R2. Now let's verify this formula using an ohm meter. The resistance of the resistor R1 is measured by the ohm meter. The ohm meter indicates 50.8 ohms. The resistance of the second resistor R2 is also measured. The ohm meter indicates 98.6 ohms. R1 and R2 are grouped in parallel and the ohm meter indicates 33.6 ohms. Here, if we apply the previous formula we deduced, which is 1 over R equivalent equals to 1 over R1, which is 50.8 ohms, plus 1 over R2, which is 98.6, we will get the value 33.52 equals to the one shown on the ohm meter. Then the formula is verified. Well, why do we connect resistors in parallel or in series? Let's check. When we connect them in series, here we have two resistors, each having 6 ohms resistance. The equivalent resistance of the grouping is 12 ohms. Similarly, when we have 3 or 4, if we compare the equivalent resistance to the resistance of each of the resistors, we can notice that it is always higher. Then, in order to get a higher resistance than the resistors of the grouping, we connect resistors in series. In parallel grouping, here we have two resistors, 4 ohms resistance each. Their equivalent resistance is equal to 2 ohms. Similarly, for these two groupings, 6 ohms, 6 ohms, the equivalent resistance is equal to 3 ohms, and in the last case, it's equal to 6 ohms when their resistance is equal to 12 ohms. So here we can notice that the equivalent resistance is always less. So to get a lower resistance than any of the original resistors, we connect them in parallel. Now let's summarize the ideas we discussed in this video. The resistor equivalent to a grouping of resistors is the single resistor which, when replacing the grouping, carries the same current under the same voltage. The formula for calculating the equivalent resistance in series grouping is RE equals R1 plus R2, while in parallel grouping, 1 over RE is equal to 1 over R1 plus 1 over R2.